ask my help anywhere you want me to pitch in, okay? Otherwise, I'll be
Yeah, yeah.
on mute. Yeah.
Sure, sure. Just share the notes and that's it.
No, are you not sharing your screen? Are you not sharing your screen?
The option is disabled for me.
I enabled now. Check now.
Like still it is coming as disabled only for me.
Okay. 1 minute. Let me stop. Then you check. Now you check.
Still I'm not getting.
Okay. Fine. Let me share. Yeah. Are you able to see?
Or wait, I can try rejoining. Just
Yeah.
one
Just
minute.
yeah.
I'll
Please
yes,
rejoin them. Yeah.
yeah.
Till that time, I'll continue. Okay. Yeah, so parsing is nothing but we are going to this is a module wherein we have almost half of the almost 15 marks of the paper from this. Okay, and
Yeah,
in
actually, I rejoined, but still, like the it is disabled for me. Okay, no worries. We'll proceed with you sharing, and I can start
sure,
explaining.
yeah,
Okay,
Saikaran, go ahead then.
okay. So, good evening, all. We'll have a look at the parsing topic. So, it is a broad topic. Like there are various methods of parsing, and like short, we are likely to get one big question in which we will be expected to draw parse trees and then give the interpretation as per the question. So, let's start with it. So first of all, there comes a concept called context-free grammar (CFG). Excuse me. So what is CFG basically? So context-free grammar. It consists of some rules in which on the left-hand side there is one single symbol, and on the right-hand side there are few other symbols. So these symbols are terminals and non-terminals. So, the set of terminals, non-terminals, and some rules mapping non-terminal with a non-terminal or a non-terminal with a terminal, they form context-free grammar. Now, what are terminals? Terminals are nothing but the words which are present in the given sentence. And all the things except non-terminals, or except terminals, are non-terminals. They include the noun phrase, verb phrase, adjective phrase, adverb phrase, and prepositional phrase. All these are examples of non-terminals. And apart from that, nouns, verbs, determiners, all these are non-terminals. Now, what exactly is this method called parsing? So, in parsing, we basically do the analysis of the words present in the sentence as per the grammar rules, and we try to see the relationship amongst those words. So, this method which does this is known as parsing. Now, while parsing, like at the end, we intend to map the words of the sentence with the non-terminal. So basically, at the end result, you get the POS tags for all these words given in the sentence. Now, there can be multiple parse trees possible for any given string. So there are some applications of parsing in real life, such as speech recognition, machine translation, optical character recognition, and grammar checking. These are few common examples of parsing. Now let's have a look at this top-down parsing. So in this top-down parsing, what we do is the approach which we follow is like we will have these rules which you are seeing on the left side of the screen. These will be the grammar rules. It will be available for us. So there is no need to remember all this. And there will be lexicons or the POS tags available for the words given in the sentence. Now we need to construct the parse tree for this sentence, and at the end the POS tagging for all these words should be available. So in the top down parsing, how we approach is we start with the rules and we try to expand the states using the given rules. And like suppose for Anu, can you scroll up a bit the previous page? Yeah. So let's say you are processing the rules, and for any one of the non-terminal, let's say NP or VP, there are more than one rule. So you will have more than one way to proceed further. So you will, pick the first one of it, and the second one of it will go into the stack, or we can also call it as a backup state. So the backup state will be acting as a stack for us in this process. And suppose when you are proceeding and the parsing fails due to any reason, then you will like pick up the last available state from the backup and proceed further with it. So since it is a stack, we will proceed in last in first out way. So let's have a look at the example to understand how it works. So we have this sentence, and now the rules are given to us. The sentence is, the old man was smiling. And the rules are given to us, the lexicons are given to us. Now let's proceed. So first rule, we will proceed in the sequence as the rules are given. So first one is as at index position number 1. Now as we can expand using rule first rule, S gives NP and VP. And now we have for NP we have 2 and 3 rules. So what we will do, we will use rule 2, and rule 3 we will put in the backup state. So if we replace NP using rule 2, we will get art, N and VP. And the alternate state will be added to the backup state. Okay. And now we will see the old man smiled. This is our sentence. So the is article here. And so we can straight away replace the article with the, and that will be removed from the current state. Now we are left with N, that is noun, and a verb phrase. So the old is again, it can have either a noun, or it can either be a noun or an adjective. So old can be noun can be replaced with old, and now we are left with only VP, verb phrase. Now it can again be expanded in 2 ways using rule numbers 4 and 5. So rule number 4 will give only V, and the alternate rule we can add again in the backup state. Now, like old man is as per the given rule in the question, man can also assume verb form. Like we don't need to like apply much brain, like how can man be a verb or a noun, like whatever is given in the question we can assume that. So man can take values of verb, so verb can again be replaced with man. Now the current state is empty, but our initial sentence had one more word, that is smiled. So this shows that our parsing has failed at this till this step. So now what we have to do, we have to backtrack using our stack. So whatever the last backup state we have, we will extract it, and we will continue with our parsing. So which state we had? We had V and P at third position. So we will extract that, and we will proceed with it. Like at the third phase, at the third position, the old man smiled. What was the sentence? Just scroll up a bit.
So the fourth place.
The old man smiled. Yeah, sir, yes, correct. The old man smiled. So at third position, it says verb. So we can replace verb with man, and now we will have one noun phrase at fourth position. Now we again have we have 2 rules for noun phrase. Just scroll up a bit for the rules. Yeah. So noun phrase has article and noun, and article, adjective and noun. Now, so like in both, if you see carefully in both the rules, there is one article at the start, but in our original sentence, we do not have any article at fourth position. So it again failed. So what we need to do, we need to again backtrack from the stack, and we will extract the last backup state, and we will proceed. Excuse me. So at position number 4, it again says article, so which is again not possible. So it again fails. Now we will extract the last available state in our backup state stack, which says article, adjective, noun, and verb phrase. So the is article, we can replace that. Like old is also an adjective, we can replace that also. And then noun and verb phrase. So man is a noun, and for verb phrase we have two ways: either verb phrase to verb at rule number 4, and a verb phrase to verb and noun phrase. So the second one we can keep in our backup state, and using VP to V we can use, and smiled can be, V can be replaced with smiled. And that's how we reach at the end of the sentence, and this successfully parses our given sentence. So now we have successfully parsed. So this same computation which we have done, so the same thing we need to represent in a tree format. So if you look at this, we start at a first index, noun phrase and verb phrase, and then we start processing the noun phrase. So noun phrase, we we proceed with it, and at the word phrase at position number 3, it can be split into two ways, and both of these ways we failed. The parsing failed. You can also see it in the previous table where we have computed. Now at the right subtree, when we started parsing the VP, so like at the 4th index of VP, we achieved the successful parse. So this way you have a successful parse tree, and rest of the sub parse trees you will have as non-successful. So this is the parse tree for our given question. So just scroll down. I mean, like, let's move forward.
No, Sai, let's ask if any question here, if any doubt, because this is a complex one,
Okay.
and all the questions further are related, similar only.
Yeah. So if anyone has any confusion or question or any step
I
which is
hope
not
everybody
clear.
understood how we incremented this 1 to 2, 2 to 3, how we are incrementing. So whenever we are finishing any word, like we are processing any word, then we are going to the next position. We have marked here 1, 2, 3. So once we processed the, here, we incremented to 2. This is important, this number here incrementing. Any doubts? Just last call. If not, we'll proceed further. Yeah, Saikran, continue.
Okay, thank you. So like in the case of top-down parsing, we can use two ways. One is the depth first, and the other is breadth first. So what we have looked now is depth first. So in this depth first, if we are proceeding with one interpretation, so we continue to expand it until we encounter failure, and then only we start exploring the alternate option available from the backup state. And the possibilities list, it is nothing but the backup state. It is maintained using stack, and since it is maintained using stack, it employs last in first out strategy to backtrack. And alternatively, for breadth first, the possibilities list, that is the backup state, is maintained using queue, and since it is a queue, it uses first in first out strategy for backtracking. And like unlike depth first, multiple interpretations are considered alternatively, and each is expanded one step at a time, like unlike depth first. So like in our question, we have used depth first for top-down parsing. Now let's look at the differences between top-down and bottom-up parsing. So like top-down parsing, it never explore options that will not lead to a full parse. Like in each of the options which we explore using top-down parsing, like full parse of the sentence is confirmed, but it can explore many options that can never actually connect the sentence. Like as we have explored above, like when we were processing at many states, we reached at a point where like the parsing was finished, but still the any of the words were left. So it explores some options which never actually connect to the sentence. Now bottom up parsing, it is opposite of this. So in bottom up parsing, it never explore options which do not connect to the actual sentence. That means in all the options available, it connects to the actual sentence. Now let's have a look at the chart parsing. Now in chart parsing, we have one advantage. In while parsing, we tend to duplicate much of the work unnecessarily by trying same matches again and again. Like suppose at any step you fail, and then you again pull up the backup state, and from there some computations you again have to redo. So all that is saved in chart parsing. So few important data structures which are used by algorithm. One is key. Key is basically the current word which we are trying to match or process or state or rule. So key is a word which we are, trying to match at that point. And active arc. Active arc is the grammar rule. For example, VP gives V and NP. For example, that rule which we are processing at that particular time, and it will have a part which is processed and some unprocessed part. So, or we can say partially matched RHS. Agenda is the unprocessed constituents in the active arc, and chart is the data structure which stores the processed constituents, like the partially processed ones, so that we can avoid recomputing the duplicate analysis. Now in the active arc, a dot separates the part which is processed and the part which is unprocessed. So we will have a look at, we will try to understand this with the help of an example. We will have an example of bottom-up chart parsing here. Now in top-down parsing, what we saw that we use the rules to arrive at the words. Now in bottom-up parsing, we will use the words to arrive at the corresponding non-terminals. So here we have this: the large can hold the water. This is the given sentence. And one important thing to notice, like you at the first step before starting the parsing, you index index before each word. Like before you start numbering the spaces 1, 2, 3, 4. This will help you to jump between the states and record like how you are parsing, like at which state the rule is failing and all that thing. So this is one important thing to note. And you will be given the lexicons or the POS tags and the rules, and then you need to parse. So yeah, let's try to do the bottom-up chart parsing for this particular example. Now, as I said, we will start with the words in the sentence. So what? Let's have a look. The large can. So the is an article. Large is an adjective. So you need to pick those rules which start with article and adjective. So we have rule number 2, which gives the article and adjective at the start. Okay. So, and the first and by default the foremost rule will be sentence giving NP and VP. This you will find in most of the questions that you will have to start with that. So that's always the first rule. And to expand the NP, then we are using the article adjective noun rule here. And the alternate rule, you will write it below it. But we are proceeding with the article, adjective and noun rule. Now, since we have finished processing the article and adjective, we will place a dot after it, and the noun is the unprocessed part. So here in this particular state, our key is the word, since it is the article, and rule is the rule, that is NP giving article, adjective and noun is the arc, and agenda is N, that is the unprocessed part. Okay, just scroll down a bit. Yeah. So we will proceed word by word of at each step. Okay. So we have finished processing the large. Now can, what all values can have? It can be a noun, auxiliary verb, and a verb. Okay. So we write all the possibilities there. Now, as per the rule, NP giving article, adjective, N. So can qualifies to be a noun. Therefore, this one is right. So till fourth, we have finished processing. So as you keep on processing, you keep on writing the rules for like above an arrow, and like start recording the corresponding POS tags in a tabular format. Okay. And from 3 to 4, I have written two more rules, that is VP giving auxiliary to VP and VP giving V and NP. So this was there mentioned in the slides of Chetana ma'am. So that's why I have mentioned it here, else this is not required. Like our this NP giving article, adjective, noun, this has covered all these three words. So you can skip this. It is not required. Just scroll down a bit. Now moving to the other words, we are finished with the large can. Now the left ones are can and hold. Okay. Again, can have an, that is, it can be a noun, verb, and auxiliary verb. And hold can be verb and noun. Now, we need to see which of the VP rules can give us this. So if we look at that VP giving auxiliary and VP, so this can accommodate this can, and it can have some accommodation for hold also. So we proceed excuse me. So we proceed with this, and at the 5th to 6th transition, we use VP to V and NP. Okay. So this covers the entire sentence, and once we are finished, we record this in a tabular format, and below the table we write the words, and at below each transition we mention the rules. So this is how the chart bottom up chart parsing works. And now the same thing like we have did in the top down parsing, we have at the end made a tree, like how we have proceeded further. Similarly, we have to make one for this also. At the end there should be a parse tree, then only it is a complete. So if we look at this as giving NP and VP, NP can have article, adjective, and noun as per the rules, and we associated the corresponding words to them. And for VP, we processed, we drilled down with the rules, and at the end, at the leaf, we have associated the corresponding words of the sentence. So this is the parse tree for this one.
I just want to add, this parse tree is nothing but the outcome of these arcs only.
Yes, right, that's right. So using this arc,
I have one question, like how this chart is formed, because Chetna ma'am didn't talk about that, how the chart finally is created.
This one, you are talking about
Yeah,
this
yeah. Any link or anything where we should refer to for this one?
one? No, this is
Any
clear.
help?
Saikran, I think you can explain this.
Yeah. So basically, as we are proceeding at each step, you are associating the corresponding POS tags in the table format, right? And let's have a look at this one. Anu, if you can zoom in a bit on the table. Yeah, works. So if you look at the bottom 2-3 rows, we have all the corresponding POS tags, and above that all the rules are mentioned. So between the first and fourth indexes, the rule which was using these POS tags, we can actually write down, we can record the rules which we use to reach there. So for example, between 3 and 4 we have can. So can take 3 possible parts of speech. So in here it is noun. That's why I have put a small tick over there. And the rule which we use to get there is NP, the rule 2. So basically in the chart we are recording which rules we have used to reach there. And this like in this example, if like in the further examples you can see that whatever is already processed, that information can, like we don't need to compute it again. We can like pull it from the already processed and recorded information present in the chart. So for example, if the is an article here, okay, so it will be stored in the chart. So when we reach at the 6th index article, so we no need to have a look again at the rules. It will be there in the chart. The processor will pick from there. So this is the advantage of chart parsing. The partially processed information, the already processed information will be recorded in chart, and using it, if something similar comes in like further, then that thing can be replaced over there. I hope I was able to
Yeah,
answer.
yeah. Actually, the question is we need to show the intermediate snaps in between, or the
No,
final
no,
snap
just
is fine.
yeah,
This
final
one.
table. Yeah, if this one will work, like, but if you are facing confusion, then you can always have intermediate steps for your own understanding. But for answering the exam, the final table showing the rules and the arrows, and at last the parse tree. These three things should be there.
So
Okay.
basically, this part, that the chart recording. So now, I mean, till here when we finished, so the large can, all the three were processed, right, using rule 2. So if you see all together, it is written as rule 2 here. Okay, and if you see here, this art and this the and water, they were processed using rule 3. So that's why it is rule 3 here, NP rule 3. So similarly, you can infer from this arc, and then above you can record which rule we have used to process. Okay,
Yeah.
I hope it is clear. Yeah, so Saikaran, we can go ahead. I think this is
Okay.
same only. The old
Yeah.
man smiled.
This
I
is
think this was from my notes.
yeah.
Yeah, so just we will
Yeah.
skip this
So
one.
we can skip this one.
Uh, this one
This
is
is
top
top down.
down. This also we will skip. We've explained one, so I think all will be similar. This also we will skip. Also, everything else is similar. These are all top down, bottom up chart parsing examples from previous exam questions. So maybe you can solve. Okay, many examples are there. These are all previous exam questions. Okay, yeah, maybe we can move to CKY parsing the cycle.
Yeah. So, so as I said earlier, there are some advantages of chart parsing is that no repeated computation of same subproblem. Like since it will already be recorded earlier, so the processor can refer to the same, and it deals well with left recursive grammars, like and it also deals with ambiguity. And here no backtracking is required, like in the top down parsing. Excuse me. In top down parsing, we maintain a stack for backtracking if we reach at any like if the parser fails, so no backtracking is required here. So now next is CKY parsing. CKY parsing is basically a bottom up dynamic parsing algorithm. So it has some constraints for it. First of all, the grammar should be in CNF. Now, what is okay? There is a question. What is CKY? So basically, CKY, like these three are the initials of three scientists who developed this parsing technique. I don't remember the name. Like we can refer to it as CKY parsing for now, for our exam. Okay. And CNF grammar rules, conjunctive normal form. So the first rule is that every LHS term in the rule should be a non-terminal. There cannot be a terminal in the left-hand side of the grammar rule. Okay. And the RHS can either be a single terminal or exactly two terminals. These are the constraints for RHS.
Two non-terminals, Sai.
Yeah, two non-terminals. Yes, sorry. So, for example, A giving B and C. So B and C are two non-terminals, and A is also a non-terminal, and NP giving N and PP, and A giving A. A is A as in the word English word A. So it is a terminal and it is single, so it is acceptable. Similarly, noun to man, it is also acceptable. Acceptable. Now, some incorrect rules are where like there is a mix of terminals and non-terminals. So these are some examples. And CNF provides an upper bound for parsing complexity, basically. So like we will get some upper bound, some idea for the complexity of the parsing.
This
Yeah.
is same whatever he has explained. These rules, okay? Maybe, yeah.
Yeah. So
Will you
yeah.
explain this example? Yeah, this maybe
Yeah.
you
Yeah.
can explain this example.
Yeah. Yeah. So, before proceeding further with this example, I want to add 2 points. Let's say we have some rules which are not in CNF. So, we convert them in CNF. Like, for example, can you scroll up a bit? No?
Yeah, here we have.
Yeah.
Yeah.
So if the first case is where the rules that mix terminals and non-terminals on the RHS. So we rewrite the rules in such a way that we eliminate the terminal and we create a dummy non-terminal. So as to so as the rule for CNF. So for example, NP gives the nominal. So the is a terminal here. So we can add a dummy non-terminal determinant giving the and replace the with determiner in the rule. So this way we can convert. And second, the rules with single non-terminal on the RHS. So we should have at least exactly two non-terminals. So we will rewrite the rules. NP is giving nominal, for example. So we rewrite nominal giving noun and PP and nominal giving determiner and noun. So we combine this and it becomes NP giving noun and PP and NP giving determiner and noun. So this way we have to rewrite and convert it into CNF. Then only we will be able to proceed with the CKY parsing. Now let's have a look at the example.
There is one more rule. If we have more than two items on RHS, that also we have to convert. So here we should not have more than two items. So it should be having
Yes.
two only. So here if you see we have determiner, noun and PP. So now we can replace noun and PP together with nominal. So then we will have exactly two non-terminals here.
Yes, that's right. I missed that one. Thanks for adding, Anu. Yeah, let's have a look at an example. So we have this sentence, the flight includes a meal. This is our sentence. So first we do the indexing for that. And next we create a table, basically include the rows and columns, include the index numbers first of all. And next we start with the we start picking up the words and we see which rules map these words with the corresponding POS tags. So for example, first word is the, and the is a determiner. So we write from 0 to 1, like the row indexes represent the first index and the column index represents from till where we are looking. So from 0 to 1, it is the, and the is a determiner. So we mention DET there. And from 1 to 2, it is flight. And flight is, if we look at the rules, it is a noun. So we include noun there. Now there is a rule which maps both of these, determiner and noun, using rule number 2. So we using this rule, we place NP there, and we can say that from 0 to 2, it is NP. Okay. And similarly, we fill up all the positions, like from 2 to 3, the word is includes, and includes is a verb, so we mentioned verb there. And there is no rule which maps n or v, so we left it there. We have left it blank. And similarly, we proceed further from 3 to 4. The word is a. A is again a determiner, so we mention it there. So again, there is no rule which maps n, v, or determiner together. So we left it blank. And at last, from 4 to 5, the word is meal. It is a noun, and we have mentioned it there. Now we have some interesting rules here. So there is a rule, determiner and noun is mapped with NP, and NP and verb is mapped with VP. So we are writing this with the given rules only. And the S is mapped with NP and VP. So this way we have created some mapping, and we have included the arrows, and this is our final tree here using CKY parsing.
Yeah.
The flight includes only.
After this chart, I did not put a tree, but I
Yes.
think we can put tree also. I think in your
Yes,
notes
yes.
you have put, maybe we can go with that example. So this is also same, she flung her on face, same what Saikiran has explained, same way we need to draw. Maybe, yeah, here, Saikiran, I think in your notes you have, right, one example with the tree.
Yeah, I
maybe
have
you
this
can.
one only. The
Same
flight
only.
includes
Yeah,
some.
then you can tell this tree maybe here.
Yeah. So as I said, like at the end, whichever parsing technique we use, at last we need to draw a parse tree. Now, like you using, just scroll up a bit, the table. Show the table. Yeah. So here, like we need to just start associating the words from the left hand side and on the right hand side. So if you look closely, this will itself give a tree
Yeah.
here. So the same tree we need to simply draw, and always in CKY parsing, you will get an upper triangular matrix. Okay, so that is an advantage here. Like it is easier to draw a parse tree from this one.
Yeah. This was covered. So this is all same. This you explained. This is same example for CKY.
Yes.
Okay. And yeah, this example create a CKY.
So any questions, anyone? Like on CKY parsing? Okay.
Okay. Next, go with this one then.
Yeah, probability context free grammar, PCFG. So PCFG, like the parsing technique is same, just that at every step, at the rules and at the words, we have some probabilities associated with it. So we have terminals, non-terminals, and a designated start symbol, and the rules, and all the set of like probabilities on the rules, and all the probabilities add to 1. Just that the concept of parsing will remain same, just that at every step the probabilities are added. And at the end, to calculate the probability of the parse tree, you simply multiply all the probabilities. For example, let's say this is the parse tree which you have obtained using CKY parsing, and at each step you have the probabilities. Now to calculate the probability of this tree, you simply multiply all these at like all the probabilities at each step. Then you get the probability of the tree. So the same computation is shown here. Like in each cell we include this probability, and to calculate the probability of sentence at cell number 0,5 we have included the calculation, and that's how we get the probability of the tree. And yeah, just scroll down a bit. There's one question.
How this is different from CKY?
Just that in the CKY parsing there is no probability attached to the rules. In this in this one PCFG, at each step, that is at each rule, you will have some associated probabilities. So just that the parsing technique is same, everything is same, just you need to compute the probability of the parse tree by multiplying all the probabilities you have obtained at each step.
I want to add here, see what is the thing here. See, if you take this example, right, here in this example, based on the rules, you will get two trees. Okay, you can get two trees, because for VP there are two rules. VP is this one and this one. So when you try to compute this, okay, so here your VP can be VNP PP. Okay, so based on this you will get two trees. Now in order to assess which tree is the best one, you cannot judge, right, like this. So if probabilities are given, then you compute the probabilities of complete tree. So whichever tree has the maximum probability, that will be your best parse tree. So that's where this PCFG is used.
Yes, and to calculate the probability of the sentence, let's say there are three parse trees for a given sentence. So the probability of the sentence will be the sum of all the probabilities of these parse trees.
Okay, got it.
Yeah, this is just a theory question. Okay, and this example is completed, Sai, and you
Yeah.
explained PCFG theory.
Yes.
And this problem, you want to go
It's
with
the
this
same.
problem? This is the same. Okay, it's the same. Yeah, then
Yeah.
evaluating parsers.
Yeah. So to evaluate parsers, we use the concepts of precision, recall, and F1 score. So precision is nothing but the ratio of the count of matching constituents with the count of the predicted constituents. Like whatever is matching with how the count of the total predicted ones. So the ratio gives us the precision. And for recall, like the count of the matching constituents with the count of gold standard constituents. So this gold standard constituents is nothing but the given observations. So this formula is same as the usual precision recall formulas which we have studied in ML and DM. And F1 score is simply the harmonic mean of precision and recall. So one small example here. So this is given the gold standard brackets. So these are the rules as, and in the brackets the indexes are mentioned from which of the index to which of the last index the rule is applied. Like the sentence is from 0 to 11th index, NP is from 0 to 2nd index, and so on. And the candidate brackets are the computed ones, like which we have computed using the parsing techniques. So these two are given, and how many are matching here? 3 are matching, which are underlined. And so to calculate the precision as per the formula, the count of matching divided by count of the predicted, which is 7. So 3 by 7 is the precision, and recall is count of matching divided by excuse me, count of the gold standard brackets, and F1 score is simply the harmonic mean of these two. So just applying the formulas to evaluate the parsers based on the given observations.
So I just want to add, there are no questions as such in previous papers on this topic.
Yeah.
So this is also a theory question. How is the probability of a parse tree computed? So he told, Sai has told, it is nothing but probability of RHS by LHS.
Yeah, probability of the right hand side of the rule given the left hand side, and the product of all this. The probability of the entire parse tree is the product of all the individual probabilities of the rules.
You want to explain this one?
Yeah. So this is the rules are given here in this question along with their probabilities. Now the first part is to draw the top ranked parse tree. The top ranked parse tree is nothing but the parse tree with the highest probability amongst all possible parse trees. Okay. So the sentence is eat the noodles with chopsticks. This is our sentence. And above them are their tags, PUS tags written. Now at the first what we will do is we will draw all the possible parse trees for this sentence. So using the rules, we have computed, we have made this parse tree. Excuse me, sorry, I'm having a bad throat, so just excuse me. Yeah. So the respective probabilities are mentioned at each step. Just scroll down. And the probability is, as I said, the product of all the individual probabilities, which
And
comes
this
to,
is to be done using CKY table, right?
yeah, using CKY. Like at the end, you can like this is the parse tree which you are which you have obtained. You can use any of the parsing techniques. CKY is just one. You can obtain it using any technique, top-down parsing, or whichever you are comfortable with, if it is not given in the question. Just that at each step, you just have to associate the probabilities with as per given in the question. Okay. So this is one probability, one parse tree, and there is one more possible parse tree present like below. Yeah, this is the alternate parse tree for the same sentence. So we compute the probability for this also. It comes to be 2.1 into 10 to the power minus 6, and this is greater than the above one. So this one is the high ranked parse tree here. Anything you would like to add, Anu?
Yeah, actually, this question is, if you see the sentence, eat the noodles with the chopsticks. Okay. Now, now this with the chopsticks. Now, if you see why we got two parse trees here, this is very important. Okay. Now, if you see here, we have two. Now, what is your S? S is VP. Now, what are the two VP rules you have? These two. Okay. So, in first tree, we have used VP rule. First one, V and P. Okay. And in the second, we have used verb VP, verb, NP, PP. So now your with chopsticks is attached to verb phrase in this one. Okay. But here your with chopsticks is attached to noun phrase. If you see here, with chopsticks is attached to noun phrase. But here it is attached to verb phrase. Now, for which tree you got the maximum? This one you got. Okay. That means you have to take this parse tree as the correct one. So this shows that top ranked parse tree with the probability which is greater than the probability of other possible parse trees, where you have the rule VP is VNP. Now semantically, if you check the sentence, with the chopstick should attach to verb, hence the resulting parse tree is the reasonable one. Okay. Now with the chopsticks, eat the noodles with chopsticks. Noodles, should it attach to noodle, or should with the chopsticks should attach to eat word? It should be attached to verb, right? You are eating with chopstick, you are doing something, eating, work is being done with chopsticks, that is eating, that the eating is verb here. So your with chopstick should not attach to noun phrase. Okay. Here noun is noodles. Okay. So that's why this parse tree value that we got as maximum is the reasonable one. That is the meaning of this one. Okay. In the question they will ask whether whatever parse tree you got, is it the correct or not, justify. So semantically, with chopsticks should attach to verb. And similarly, if you see, ask the man with chopsticks. Now here in this case, the sentence meaning is ask somebody who is having the chopsticks. That means your with the chopsticks should attach to noun phrase here. Now when again you calculate the probabilities, now here again this is the maximum, right? Now but now if you see, this top ranked parse tree that we got is not the reasonable one, because the sentence that is given in this sentence with chopsticks should attach to noun phrase, not the verb phrase, because here the meaning of the sentence is ask that man which is having the chopsticks, man with chopsticks. So here with chopsticks is related with man, not with ask. I hope this is clear.
No, I have a question, please.
Yeah.
Yeah, regarding the chopstick,
Yeah.
why it shouldn't be attached to the verb in the first one? Why it should be attached to the noun?
It should be attached to
Sorry,
the
why it should be
verb
attached
phrase.
to? Yeah, why?
So how will you do? How will you? I mean, semantically, what should be the sentence here? Eat the noodles with chopsticks. Like you are asking to eat the noodles with the chopsticks. I know you are trying to say that noodles should be attached to with chopsticks. Like noodles should be eaten with the chopsticks. But
Absolutely.
generally, in real world, how we take this sentence, like you are eating the noodles, you how will you interpret this sentence with the chopsticks? That means you are eating with, right?
Yeah, okay. Eat with chopstick, maybe it makes sense.
Yeah,
But saying eat chopsticks, it doesn't make sense, correct?
I'm
Eat
not saying eat
chopsticks.
chopsticks, a total sentence with the chopsticks, right?
Okay, okay. Thank you.
Yeah,
Thank you.
yeah. So this will be little tricky. Maybe we need to try to understand in exam how the question will be. But this is one question that has come in the exam. Okay. Yeah, Sai, you can continue. I think this is similar only, right?
Okay. Yeah.
Or you want to explain?
No, this is similar only in this also. Like
Yeah,
for yeah, like at each step we have computed the probability. In this, the sentence is ask the man with suits.
yeah.
So similarly, we will draw the possible parse trees and we will compute the probabilities. So like there are two things here. One is like actually as per the concept, which for which of the case the probability is higher. But like if we look at the sentence meaning, which actually seems correct. So there's a comparison and contrast between these two things. So the sentence can be anything in the exam. So like as Anu explained in the for the previous question. So similarly, we need to like do the reasoning for like as per the question, as per the sentence of the question.
Yeah. What is this one? Given a tree bank, how would you determine the
Yeah.
probability?
Grammar.
Yeah, this one you can explain, Sai. This is how to determine the probability.
Yeah, yeah.
Okay, this is same only, right? Just multiplying. Yeah, maybe you
Yeah,
can
like
explain. Yeah.
just we draw the parse tree, and each step we associate the probabilities, and we do the product, and we get the probability of the tree. And just to reiterate, like if there are multiple parse trees, and in question it is asked like what is the probability of the sentence, then it will be sum of the probabilities of all the parse trees. Okay, just a small note for this.
So you mean it will be sum of the all the parse trees we need to draw, and it will be sum of all the probabilities of these parse trees, right?
Past trees, the probability of the sentence, yes.
Okay. Yeah.
Then now let's move to dependency graph. So in a graph we have two things. One is the set of nodes represented by V, and set of arcs or edges, you can say. So these two things make a graph. So arc, like let's say there are two words, Wi and Wj, and from Wi you are going to Wj, and the association is marked with a label D. Okay, so the arc will be like it can be written as arc of Wi, and D is the label, and Wj. So here in this case Wi will be the head, and Wj will be dependent on Wi with label D. So this is the representation which we will be using in the following questions.
Just a minute. Sai, can others mute, please? I see somebody is unmuted. Yeah, continue.
Yeah, like I still see some people are unmuted.
Yeah, now you continue.
Okay. So there are few conditions for the dependency graph G. So first of all, it should be connected. So by connected, we mean, let's say like there are two nodes I and J. So there should be a way to reach node J from I. Okay. So this is one condition. Second, the graph should be acyclic. So by acyclic, we mean that there should not be any loop in the graph. So if from I to J there is one mapping, then there should not be a weight from J to I. Okay. Now, if like the G should obey the single head constraint, like from, let's say, from I to J you are going, and there is this association. So I will be head for J, then there should not be any second head for J. Like there should be only one head for any word. Okay. And fourth is projective. This is important to see. Like what does this rule says? If like I to J, then J to K for any K such that both J and K should lie on the same side of I. So this we can see with the example below. I saw a girl with a telescope. So this is our statement, and the dependency arrows are shown there. So let's say let's consider the word saw. Okay. So from saw you are going to girl, and from girl you are going to A. So these two lie on the same side of saw, like on the right side. So this rule is valid here. So this is the rule of projectivity. Like from one word you are going to another word, and from the second word you are going to a third word. Then the second and third word should lie on the same side of the first word, the head word. Okay. So this is the rule of projectivity. Now, what are the methods of dependency parsing which we will be looking here is, one is the maximum spanning tree, that is the graph algorithm, which comes under graph algorithms. And the other one is deterministic parsing. It is also called as MID parser, or just scroll down a bit. Arc, there is one more name for it, arc eager parsing. Yeah. So there are other methods also, but that are like out of the scope of this exam. So we will only be focusing on these two. Okay. So let's have a look at the algorithm of arc eager parsing, and then we will look at an example for it. Now, arc eager parsing, or it is also called as MID parser. So it will have like four kinds of steps: left arc, right arc, reduce, and shift. Now, please listen carefully, everyone, because these four steps needs to be clear in order to attempt any question. So, and it is very easy also. Just we need to know in which arc, which kind of operation we have. Okay. So we have a stack, we have a buffer, and we have the set of arcs A. Okay. Now, so in stack, like in the stack and in the buffers, at any state, some words will be there. So if the last word of, like, all the four conditions like depend on the last word of the stack and the first word of the buffer. Like these are our words of interest: the last word of the stack and first word of the buffer. So for left arc, like if this last word of the if the first word of the buffer is the head for last word of the stack, that is wj to wi, there is some association, then we remove the last word from stack. This is the left arc. Okay, I am again repeating. If the last word of the stack, if the first word of the buffer is like dependent on the last word of the stack, then we remove the last word from the stack. This is the left arc operation, also denoted by LA. And for right arc, if the last word of the stack is the head for first word of the buffer, like the mapping is wi to wj, this is the relation, then we remove the first word of the buffer and add it to the stack. This is the right arc operation. Okay. Now, reduce operation. So reduce operation is like the last word of the stack is not related to buffer, but let's say any other word is related to, any other word of the stack is related to the first word of the buffer, not the last word. Then we remove the last word from the stack. This is reduce. Okay, so all this we will see with the help of an example. Just keep the main points and differences in mind for idea, and with each in the question we will look at it. and last is the shift operation. What does shift say? Like if like there is no word of the stack is related with the first word of the buffer, then add the first word of the buffer to the stack. That is shift. We are shifting the word of the buffer from the stack when no word of the stack is related to the buffer. Or if the stack is, you can also say one case is when the stack is empty, then obviously there won't be any word, then nothing in the buffer will be related to the stack, then we shift the first word of the buffer to the stack. So these are 4 operations: LA, left arc, right arc, reduce and shift. LA, RA, RE and SH. 4 operations we have. Now here comes the question. Let's have a look with the help of an example. So like these, you will be given this a sentence, and you will be given the dependencies. So the dependencies are your arc, okay, like from which word you are going to which word. So the source word is the head, and the destination word when you go there, so that is an association which is marked by a label. Okay, now let's try to parse this one. So first, initially the stack will be empty and all the words will be present in the buffer. Okay, this is the first step. Like everything will, all the words will be present in the buffer and the stack will be empty. Now see carefully, like the stack is empty and buffer has words, so no word in of the stack is related to buffer. So as per the rules, we do shift here and we record the same above on transitions. So what we need to maintain is, we need to maintain the transitions, and at the end you need to report this as the answer along with these steps. Like at each step, what is the stack, what is the buffer, what are the arcs, and at last what is the transition sequence. This sequence is important, which you need to record. Okay, now so in the first step we did a shift, so we wrote sh there, and second and third steps I have combined in, so I'll explain it slowly. So second, now what after shifting he.
1 minute, Sai, maybe you can use another one example if you want, or is it okay?
Yeah, it is okay, it is okay,
Okay.
it's totally fine. Now, so just one step is missing here, rest everything is fine. So now we shift he in the stack, and the buffer will have sent her a letter and dot, that is a full stop. Now he is related to sent, like sent is the head word and he is the destination. So which kind of like operation will we have when the first word of the buffer is the head and the last word of the buffer, last word of this, it is related to last word of the stack, it is the left arc. Okay, so we shift the first in the left arc. What we do, I hope people are getting here. Like you just need to remember each operation very carefully: the left arc, the right arc, the shift and reduce. You need to be clear about the differences between them, and then only you can, you know, approach any question. Okay, so you shift basically the first word of the stack to the sorry, first word of the buffer to the stack. Okay, now this is our, and whatever arcs you are using, you record it in the third column, arcs. Okay, now we have sent her, sent is in the stack and her letter is in the buffer. Now so sent is the head and her is the destination. So the first word of the stack is related with last word of the buffer. This is a right arc operation. So in the right arc, we move the first word of the buffer to the stack and record the same in the arcs. Again, is there a relation between her and A? There is no relation, right? As per the sentence. So when nothing in the stack is related with nothing in the buffer, so what we do? We do a shift. So A is shifted to the stack. And now what are we left with? Letter and dot in the buffer, and sent her A in the stack. Now, is A related to letter? Yes, it is related. Like the first word of the buffer is related with the last word of the stack. So what is this? It is a left arc. So what we do in the left arc, we remove the last word of the last word of the stack. So two ticks are missing, Anu. Like you need to put a tick on RA and SH also.
Yeah, sorry.
Yeah. A left arc. So we removed A from the stack. Now we are left with letter and full stop. Now, is letter related with her? No. Is letter related with sent? Yes, definitely. So one of the, not the last word, but one word of the stack is related with the first word of the buffer. So this is the case for reduce. So what we do in reduce, we just remove the first word of the stack. So her is removed. Now what are we left with? Letter and full stop in buffer and sent in stack. Is sent related to letter? Yes, it is related. So it will be a right arc. First word of stack related with last word of stack related with first word of buffer. So it will be a right arc. What happens in right arc? The letter will be shifted to stack. Now only full stop is left. So does letter relate to full stop? No. But sent is related to full stop. So if any, not the last word of stack, but one of the other words of stack is related to the first word of buffer, what we do? We do reduce. So in reduce, what happens? The last word of the stack is removed. So now only sent is left in the stack and full stop in the buffer. So is sent related to full stop? Yes, it is related. How it is related? Right arc. So in what happens in right arc, the buffer, the item in the buffer is shifted to the stack. And like you can leave at this step, but in some ma'am also left her example at this step, but it is good that you include two reduce operations also. So when the buffer is empty and the stack is full, so you need to basically empty the stack also. So how to empty the stack here? So nothing in buffer is related to nothing in stack. Okay, so we do the reduce here. Excuse me for that. So then, so what you can remember is at the end, like the number of reduce operations to be appended at the last will be the number of words you have at the stack after the buffer is empty. So just to add this point, I purposefully left that so that we can stress over this point. Okay, so at the end you have got the transition sequence. You have got the states at each step, the stack, buffer, and the arcs used, and this is what you need to do. So just remember the left arc, right arc, reduce and shift operations, the conditions for them, and then practice 1 or 2 questions. You will get it, or you can have a look at this, so you will get it. So it will come by practice, so nothing to worry here. Okay, so any questions at any step or any operation, left arc, right arc, any confusion, anyone? I hope you understood this.
Anyone has any doubts here? Because this is important, very important actually. This is there in every question paper. Okay, if this is clear, then we'll proceed. So these are again same for arc eager only. More questions are there. Everything is same. Okay, so no need to repeat. Yeah.
So we can have a look at this one. So like we have in the last session, what we did is we parsed that using dependency parsing. We maintain the state, we maintain the stack and buffer and the arcs which we used. So like let's see this question. It is a bit different. So whatever operation which we are applying uh, amongst the four operations, that can be considered as one of the classes. Okay, and the state of the stack and buffer, they can be considered as one of the configuration. C0, C1, they can be represented as any configuration. So now let's see this question. The features are given. They, sorry. The features are: the stack is empty, the top of the stack is noun, and top of buffer is verb. Top of stack is verb and top of buffer is noun. So these are three features. So in when these three when the condition is met, you can mention it as 1, else you can put it as 0. Okay. Now we need to initialize the weights of all the features. Okay, so to 5, this is the initial weights, we can say, for the features, except that in all of the above cases you give a weight of 5.5 to left arc. So basically in this question it is assigning weight to the operations, and it has given more weightage to left arc operation. Okay, now define feature vector and initial weight vector. Use arc edger parsing technique. This is our question. So at the end, it expects how a feature vector will be represented and what will be the weight vector. Okay, so let's see it. So the features conditions we have. Okay, so for any of this state, let's like list down all the possibilities which can happen. Okay, so for there are three features, C0, C1 and C2. Let us represent it using this, and there are 4 classes: LA, RA, RE and SH, corresponding to the 4 operations. So all those we have represented here as f of C and T, as a function of C and T. C is nothing but the state, and C is nothing but the features, and T is the transition operation, either left arc, right arc, shift or reduce. Okay, now as per the condition given, all the LAs have been assigned a weight of 5.5 and rest all are assigned weight of 5.0. So this is our starting weight vector. Okay, now so at each of that, as per the given feature conditions, we we write down the values of the feature vectors numerically. So wherever those features are, those conditions of the features are met, we represent it as 1, else we represented it as 0. Okay, so like as we have for LA, like for C0 LA, it will be 1 and rest will be 0. And similarly for RA, so wherever it is being matched, so that part will be mentioned as 1 and rest will be mentioned as 0. Now what we need to do is we need to multiply the weights with the features. So this is an important step, like the weights multiplied by features. So this step we will use in further in the further algorithms also, which we are going to discuss further. So when we multiply it, what is happening? Just scroll a bit. Scroll a bit up. Yeah. So yeah, just scroll down a bit. Let's just so that the vectors are visible. Yeah. So this weight is being multiplied with f of CLA and f of CRA. Okay. So when this is when it is multiplied, so at the first position we will get 5.5, and for f of CRA, when it is multiplied with W, at the 4th position we get 5. Okay, so 5.5 is a greater value than 5. So the recommended transition would be LA. Just scroll down a bit. So basically we are just multiplying here in this, and but the given, as per the given observation, the transition is SH, but our computation says that the transition should be LA. So here there is a difference. So what we need to do, we need to update the weights. How we are updating the weights? This formula, W is equal to W plus F of C T naught. T naught is nothing but the given observation minus F of C comma T star. T star is what we have computed, and T naught is what we have been given. So given it is SH and computed it is LA. So we again do the computation here. W plus this F of C T naught. We represented it using this array, and similarly F of C comma T star we again represent it, and now this is our new vector. So just nothing. So basically in this type of question, this was only one. So I thought to mention it here. So what we are doing is, in the question you will be given features, and use like corresponding to those features you need to assign the values 0 and 1 wherever it is there in the possible combinations, and then you need to multiply with the initial weight vector, and then you need to check. And this is how you need to find you will find the last new vector. So there were only hardly one or two questions, so like not much probability, but at least you should be aware of the concept, like if such question comes, so how will we proceed with it? Yeah. So some like we will use similar techniques for upcoming algorithms where it will be more clear. Excuse me. Yeah. So now we have a multi-digraph. So what is a multi-digraph? So multi-digraph is a digraph where multiple arcs are there between vertices. So there is not just one way between two nodes. There can be multiple ways, as you can see. So the directed spanning tree of a multiple digraph is a subgraph of the main multi-digraph. So we like going forward, we will be interested in only computing the maximum spanning tree of the given multi-digraph. So what is a multi-digraph? It is a graph with multiple like edges between any of the two nodes, and one of the possible subtree, or we can say directed spanning tree, will be a maximum spanning tree, which we will be interested in finding. Now, in weighted spanning tree, each arc has a weight which is positive assigned to it, and the total weight of the graph can be calculated as sum of all the weights of the arcs. Okay. So as in, if you remember in PCFG, like everything was same. That we obtained the tree using CKY parsing, and we just attach the probabilities, and we just multiply it, and then we get the total probability of the tree. So similarly here in this diagram, we have the entire like each edge we will have the weights assigned to it, and the total weight of the graph would be the sum of all the weights. Now let's come to this algorithm. It is an interesting algorithm, Crew-Liu-Edmonds algorithm. So each vector in graph selects incoming edge with highest weight. Okay, so there will be since there will be multiple edges incoming to any particular node. So to find the maximum spanning tree, we select the edge with the highest weight, and the resulting tree should be a maximum spanning tree after the selection. Let's say if it is not, then there should be a cycle. Let's say you pick up a digraph, you select all the maximum vertices, maximum weight edges, and then you get a cycle. Then that will not be a maximum spanning tree. You need to compute more. So you need to identify the cycle and contract it into a single vertex, and then recalculate the weights going in and out of the cycle. So this step is where the computation is required, and the questions will also revolve around this. So let's try to understand this using this example. So as you can see here, we have 4 words. In fact, only 3 words, and one is a root. So root is the only node where there is no incoming edge. Rest all nodes will have incoming edge. You can see that. John saw Mary. So there are only 3 words and there are multiple edges. Now, first step is, as we said, find highest scoring incoming arc for each vertex. Incoming arc, okay, we need to be careful. So let's pick the word John. So how many incoming edges are there? One is from saw 30 and 11 is there, and 30, 11 and 9, 3 are there. Okay, and which one is the highest? From the one from saw. So we will keep it. Let's go to saw. So from saw, for saw we have one from John, that is 20, 10 and 0. So the highest is 20, so we keep it. Let's go to Mary. For Mary, the highest is 30 from saw, and there is one from 9 and one is 3 from John as well. So we keep 30. So using this, we have reached this subgraph. But there is one problem here. We have encountered a cycle. So this is not the maximum spanning tree. So what we will do here is, we will consider John and saw as one single entity and we will recompute the subgraph. Like we will again recalculate the weights. Okay. So John and saw, we will be taking it as one entity and then we will be again recomputing the same procedure. So let's take it. So Anu, can you scroll up a bit, the main question? Yeah. So now John and saw has some like edges which they are exchanging in between them, and now we need to consider them as one single vertex. Okay. So how we will compute the incoming edges to them? So what we will do is, like individually, whatever incoming edges we are seeing there, so that we will calculate. So for John, one is 9, that is for sure. One is 11 from Mary, that is for sure. And if you notice, one is from root via saw. Okay, so from root it goes to saw, and from saw it goes to John. So we will write it as 10 plus 30. We will add both of them, 10 plus 30. So we will mention one edge coming from root as 40, and there is one more. That from root, if you notice, one 9 edge is coming, and then one from John to saw, 120 edge is also there. Okay, so if we add both of them, that will be 29. So on John and saw combined, we have 2 weights available. One is 40 and one is 29. So as per the first step, we need to pick the highest one. So we pick the 40. So is this clear how we are getting 40 here? Because this is known as the contraction step, and this needs to be clear.
Can you please run it through once again, this how it 40 came out?
Okay. So till the cycle part, any question? Like when we were getting the cycle? That is clear, right? Yeah. So you just select at the first step, you just select whatever the highest incoming edge is there on each node, and then mention that. So the resultant, if it has a cycle, then you need to contract the 2 of the nodes which forms a cycle into one node. Now, here is the tricky part. So when you note the incoming edges from root to both of them, so you are seeing the incoming edges on both of them, on John as well as on saw. So if you if you look at John, so one is from root to saw, which says 10, and then from saw to John, which says 30. Okay. So if you add both of them, it becomes 40, right? Similarly, one from root to John and from John to saw, that is 9 plus 20, which is 29. Okay. I'm not sure who asked that question. So
Yeah,
is
yeah,
this
yeah. Thanks, sir. Thanks.
yeah? So you have one option as for like 40, one option as 29, and there is one option from Mary, like from 11 to so if you look at from Mary to Saw via John, so 11 plus 20, that is 31, and one option from Mary to Saw to John, that is 11, sorry, 0 plus 30, that is 30. So there are four options available, four like ways available. So amongst all of them, the highest one is 40. Okay. So the same, so that's why from root we have mentioned to John as John and Saw as 40 from root. So from each node we need to mention which is the highest incoming edge on the joined vertices. So from root, if we see one was 40 and one was 29, so we selected the 41. We are seeing John and Saw as one single vertex. So that's why in the subsequent step, it was mentioned as 40 from root to John and Saw. Okay. So just scroll down a bit. So at this point, I assume that you understood how this 40 came up. So similarly, you need to see for the outgoing edges from that node, from that joint node. So how we calculated from the incoming ones, similarly the outgoing one also needs to be looked. So it is 30, mentioned as 30. So why it is 30? Similarly, you need to find all the ways how it is going out from John and Saw to Mary. So and that's how excuse me, sorry. You mentioned it there, and then from Mary to John it is 31, and from yeah, just there only, yeah, from root to Mary there is one edge is there. Just scroll up a bit only. We are at step 2 only right now. Step 2, yeah. So 40 we have got, 30 we have got, 31 we have got, and from root and Mary there is one edge, 9. Okay. So if you have reached this step, then you are almost there. Like this is the main step. Okay. Now, another rule says like there should be only one incoming edge on each node. Only one incoming edge. So for that, again, you need to select the one with the highest weight. So wherever you need to select the edges, you need to select the one with the highest weight only. That is the first step of this algorithm. So just remember the one and you will be able to proceed forward. So for Mary, if we see there are two incoming edges. So we keep the one with 30 and discard the 9 one. And on John, there are two. One is 40 and one is 31. So we keep the 41 and discard the 31. So we have these two. Now the cycle is eliminated at the step 3. Now, but this was not our original graph. In our original graph, John and Saw were two different. So we expand these two vertices how they used to be. So how this 40 was initially, how this 40 came. There was an edge from John to Saw, which had 30 weight, and there was an incoming edge from root to Saw, which had 10 weight. So this was the initial, like how we calculated 40. We are again relooking into it so as to expand this. And so similarly, we just mentioned that we break that 40 into 10 and 30, and this is our final graph. So basically, this is our maximum spanning tree for the given question. So to reiterate, the first and foremost important thing which you need to remember is you need to select the incoming edge on any node with the maximum weight. Okay, and at step 2, you might encounter a subgraph having a loop, and if such is the case, then the vertices which forms the loop, they will be considered as one single vertex, and the incoming weights will be recomputed. And how you recompute? you also take into account the weights of the vertices in between those two joined vertices. Like like in the case from root to saw and from saw to join, there was one vertex, so we added them, and then that added to be 40. And similarly, another was there, but that added to 29. So again, rule number 1: select the edge with the highest weight. So we kept the 41 and discarded the 29 one. And similarly, there is one more rule. At the last, there should be only one incoming edge on any of the node. Okay. So that way we discarded this root to Mary, this 9 edge, and we were left with. Anu, can you please scroll down to step 3?
Yeah.
Yeah. Just a bit. Yeah. Perfect. So that way we arrived here. And but this was not our, this is like you are almost there at the finish. So here, this was not our initial graph. Initially, John and Saw were separate. So if we look at the incoming node, incoming edge from root to John and Saw, it is 40. But how this 40 came? It was actually 10 plus 30 from Saw to John. So that's how we decomposed it and we expanded it, and this is our final graph.
Maybe Sai, you can take up this example also so that it will be more clear. This is this one more.
Yes, yes. Just
This is the
expand
end.
it.
This is the last example. Maybe this
Just-
this is important topic. We seeing every question paper. It has a question.
Yeah, yeah. So this is our like multi-digraph given. I saw a girl. Okay. So what is our first step? Select the edges with the highest weight. Incoming edges with the highest weight at each node. Okay. So at I, if we see, we have 1 6 and a -2. So we select we select the 6 one from saw to I. And at saw, there is one from girl, that is 2, and one of -1 from I. Select the one with the highest weight. From girl, we keep the 2 1. Okay. The edge with 2 value. And if we look at the node girl, so we have a 5 and a 4. So there we select the 5 edge. And for A, we have a 1 and a 7. So we take the 7. So here we have reduced it, but here there is a loop. Okay. What is this loop? A and girl. So what we do here, we again recompute we consider it as one node and recompute the weights of the incoming edges. So if we look from saw to both of them. So from saw there was another edge with weight. Just scroll up a bit to the question with value 4. There was one edge with value 4 from saw to girl. Okay. This one, yes. Now we can come down. Yeah. So from that will be added to this. Just excuse me for a minute. Sorry, having a bad throat. Okay. So yeah, so we compute that value from 4 from saw to girl. We have this 4, and if we compute for A, it will be from saw to A. It will be 4 plus 7, which is 11. So from saw to girl, it should in the contracting step it should be 11. It's a small typo here. Yeah, this should be 11. Yeah. Okay. So now we have this, and there are no cycles present. So this is we are almost at the end. And now we need to expand it. How we will expand it? We will, how it was earlier, the girl and A. if we have a look, how did this saw to girl A came at this 11? It was 4 plus 7. 4 from saw to girl, and from girl to A it is 7. So we expanded it. So this will come by practice. So there are not much rules for it. The rules are simple. Initially select the edges with the highest weights, highest incoming edges with the highest weights, and then if it forms a cycle, consider both the nodes as one single node and recompute the incoming edges on those joint nodes, and eliminate the cycles if there is any, and every node should have exactly one incoming. If these conditions are satisfied, then you are good to expand the joint node like how it was before. That was all. Hope it is clear.
Yes, we have reached the end. Any questions on this topic?
Yeah, just wanted to know one thing. Just to confirm whether we have, expanded or contracted it well. So like we have it in 11 when we, the green colored 11 that you made. So when we open it up, it will become 4 and 7. So it has to be, we can do a back check that whether we have done it
Yes.
right or wrong.
Exactly. It will like the edges in the resultant maximum spanning graph. It will be a subset of the initial question only. The edges present will be one of those in the initial question. Like the weights are not going to change.
Wonderful. Thanks, sir. You guys have done a wonderful job.
Thanks for that. I just want to add one thing. In the exam key, I have seen that the marking will be based on the steps that you have mentioned. Like here, you cannot go directly from this step to this step. Okay, so there is a mark for each step. So you should be contracting and then expanding. Okay.
Yes, these 3 steps should be there. The first step should be the one with the cycle, where you have selected the incoming edge with the maximum weight at each node, and then you identify the cycle and do the contraction. That's a contraction step, and third is the expanding step. So these 3 steps should be there, with little bit of reasoning, like why you are going for contraction, because there is a cycle, and after contraction you will be expanding it. So that's it.
Yeah, I think Sai, anything else you want to I think you are also done, right?
Yes, this was the last question, right?
Yeah,
So yeah.
I will correct this part. There is some wrong actually. I am supposed to put 11 here. Okay, I'll correct this and then I will share these notes across. Maybe you can go through, and if you see anywhere any ambiguities, report it to us also, so that we will also correct, because some of the questions we have copied and there is confusion. I understand with what madam has taught and what is there in the answer key. I'll just stop the recording and then